Welcome everyone to today's episode of AI on AI, where we explore cutting-edge innovations in our field. Today, we're diving into the world of automating code generation from scientific papers with PaperCoder.
Thanks, host. I'm excited to discuss how PaperCoder uses a multi-agent framework to decompose the paper-to-code process into three distinct yet interconnected phases: planning, analysis, and coding. Think of it as a highly organized assembly line for software creation.
Absolutely. At its core, the planning phase constructs a high-level roadmap, including system architecture diagrams and file dependency maps, resembling the way a seasoned project manager lays out milestones before the development sprint begins.
From a business standpoint, this is transformative. Companies can now overcome the notorious reproducibility bottleneck in ML research, saving time and money while accelerating innovation in a competitive landscape.
And on the technical front, the system is impressive. By utilizing specialized LLM-based agents for each phase, PaperCoder effectively mirrors human software engineering practices. It's like having a team of expert coders working in perfect harmony, each tackling their part of the project.
I'd add that the analysis phase ensures every generated file is scrutinized for functionality and dependencies. It's not just about generating chunks of code. It's about crafting a complete, cohesive repository that adheres to best software engineering practices, even outlining configuration files and UML diagrams.
That's a great point. It's interesting how the planning phase feeds into the analysis stage, which in turn informs the actual coding step, much like constructing detailed blueprints before laying a building's foundation.
Exactly, host. And this structured approach minimizes errors. The paper highlights that sometimes only about 0.48% of the code required human modifications for successful execution, an impressive metric that shows how closely the generated code aligns with expected standards.
To put it in perspective, imagine the traditional reverse engineering process in research. It's often messy and time-consuming. With PaperCoder, the code is modular, dependency-aware, and comes with built-in configuration files, making it readily executable.
For business leaders, this means reducing the overhead associated with reproducing peer research. Think of a retail analytics firm that can now deploy advanced ML techniques faster and with less risk, leading to faster go-to-market strategies.
On the technical side, the system's use of open-source frameworks for diagram generation, file ordering, and configuration management really underscores its scalability. It's like having a smart engine that auto-tunes itself with minimal human intervention.
And here's an unexpected twist. I've heard some critics argue that complete automation might leave little room for innovation. But in reality, this kind of technology frees up human experts to focus on higher-level innovation rather than battling dependency errors and manual debugging.
Ooh, interesting contrarian view there, Expert 5. It's like how automation in manufacturing freed skilled workers for more creative tasks. The same principle seems to apply here with code generation.
Exactly. With the system's three-stage pipeline, each phase builds logically upon the previous one. The overall plan informs the architectural design, which then creates a dependency-aware task list, a robust structure that ensures consistency and accuracy throughout the development pipeline.
And the evaluations are rigorous too. The paper demonstrates that PaperCoder's repositories consistently outperformed naive baselines like just using the abstract or full paper text. The use of benchmarks like Paper2Code and PaperBench Code Dev gives it a solid credibility boost.
Strategically, this technology could revolutionize R&D processes in many industries. For example, a fintech startup might rapidly prototype a new ML-driven fraud detection system by automatically generating reproducible code from the latest research papers.
I'm particularly impressed by the integration of configuration file generation. By converting experimental hyperparameters into a human-editable config.yaml, the system ensures flexibility while keeping fidelity to the original paper's methodology.
And let's not forget the human evaluation aspect. Comparing the generated code against official implementations and having subject experts rate them. That layer of validation reinforces the reliability of the automated process.
It sounds like PaperCoder is setting a new bar for both reproducibility and automation in ML research. The interplay between detailed technical design and practical business impact is truly remarkable.
It certainly is. By emulating a structured software development lifecycle, the system reduces the common pain points researchers face when code isn't available, paving the way for more rapid and open scientific advancement.
And the modular design means improvements can be iteratively applied. Each agent, whether handling planning or coding, can be fine-tuned independently. It's like updating an app through modular plugins without overhauling the entire system.
For business leaders, the implications are significant. Enhanced reproducibility does not only drive academic progress, but also accelerates commercialization cycles. Faster validation of research ideas means more nimble innovations in the market.
I also appreciate how the system adheres to best practices in software engineering. The use of UML class diagrams, sequence diagrams, and clearly defined file dependencies ensures that even complex code bases remain maintainable and extendable.
And there's a bit of humor in it, too. It's almost as if the model is saying, "Hey, expert 2, I've got your back. No more scrambling to piece together code from cryptic research papers."
Ha! That's a good one. It really captures how this technology transforms what used to be a laborious task into something almost effortless.
In summary, PaperCoder exemplifies how LLMs can bridge research and implementation. It's a major step toward automation and code generation that could reshape our approach to scientific discovery in ML.
Agreed. With its robust multi-agent framework, modular design, and impressive evaluation metrics, it's not just incremental progress, it's a paradigm shift.
And for leaders, that shift represents a compelling competitive advantage, streamlining the innovation pipeline while reducing overhead.
I'm excited to see how this technology evolves and what new applications it will spawn in various industries.
Me too. As we move forward, the blend of automation and human oversight will be key to harnessing this power effectively.
That's a wrap for today's discussion on PaperCoder. Thank you to all our experts for a rich, insightful conversation blending deep technical analysis with strategic business perspectives. Until next time, keep pushing the boundaries of possibility in AI and software engineering. Welcome back to part 2 of our deep dive into PaperCoder. Today, we're shifting gears to explore the intricate technical implementations and their real-world business implications.
Let's kick off with the technical nuts and bolts. PaperCoder's 3-stage pipeline is fascinating. Its planning stage meticulously generates an overall implementation plan, architectural diagrams, and file dependency orders, much like drafting blueprints before constructing a high-rise.
Absolutely, and from a coding perspective, each stage leverages a customized LLM agent. For example, in the planning phase, one agent analyzes the paper's methodology to design UML class diagrams and sequence diagrams, ensuring that even complex interfile dependencies are clearly mapped out.
From the business standpoint, this structured decomposition transforms research into actionable projects. Imagine a scenario where a pharmaceutical company rapidly reproduces the latest bioinformatics research without reinventing the wheel, accelerating time to market for life-saving drugs.
Diving deeper technically, the analysis stage breaks down file-level responsibilities. It analyzes classes, functions, and their interactions while ensuring that generated configuration files like config.yaml correctly encapsulate hyperparameters such as learning rate and batch size as outlined in the paper.
And let me add, it's not just a simple text-to-code conversion. The system generates dependency-aware code that gets validated against benchmarks like Paper2Code and Paperbench Code Dev, ensuring that only about 0.48% modifications are necessary, which is a real testament to its robustness.
It's almost like PaperCoder acts as a conductor, orchestrating a symphony of microagents, each one playing its part perfectly so that the final output is coherent, maintainable, and ready to run without major fuss.
Exactly, host. The multi-agent collaboration is designed to mimic agile software development, where the planning, analysis, and coding phases are analogous to sprint planning, iterative development, and continuous integration. In essence, an automated agile framework.
And on the business side, think about how this level of automation can significantly reduce R&D costs. The traditional process of code reproduction is labor-intensive and error-prone. But with PaperCoder, companies can re-implement state-of-the-art research in minutes rather than weeks.
To illustrate, consider a fintech company needing to integrate the latest anomaly detection techniques. With PaperCoder, they can automatically generate a reliable prototype from a research paper, test it against live data, and iterate quickly to stay ahead of market risks.
Technically, the implementation deep dive reveals some clever design choices. The structured output of the planning phase isn't just informative. It directly feeds into generating detailed, file-specific analyses, so each file's logic is documented and its dependencies resolved before code is even written.
And this also opens up opportunities for iterative refinement. If an error is spotted in the dependency graph, only that specific module needs tweaking, akin to changing a faulty spark plug in a car engine rather than rebuilding the whole system.
I love that analogy, like being able to swap out a component in a luxury sports car without disassembling the entire drivetrain. It's efficient, precise, and obviously engineered for high performance.
Building on that, the abstraction layer created in the planning stage allows developers to integrate standard open-source libraries for tasks like dataset loading, model training, and evaluation seamlessly, ensuring scalability and maintainability across projects.
And to add on a technical note, the design emphasizes clear API contracts between modules, using well-defined interfaces. For instance, the model's forward method is explicitly typed to accept tensors and return tensors, greatly reducing integration risks and debugging time.
From a business application perspective, such rigor means that multinational companies can rely on the technology to generate reproducible code in highly regulated industries, cutting down on compliance risks and accelerating product deployment.
Not to mention, the use of modularized configuration files enables dynamic fine-tuning. Business units can adjust hyperparameters based on empirical feedback without re-architecting the entire codebase, which is a huge win in fast-paced innovation environments.
And sometimes, as a contrarian view, one might argue that over-automation could stifle creativity. But in this case, by offloading routine coding tasks to PaperCoder, experts are left more time to innovate strategically and explore novel research directions.
It's fascinating to see how the blend of automated technical rigor and strategic business agility can lead to a paradigm shift across industries, from academic research to enterprise-scale deployment.
In summary, the technical deep dive into PaperCoder reveals not only the elaborate interdependencies managed by its multi-agent system, but also how such innovations can be leveraged for accelerated, cost-effective industrial research adoption.
And as business leaders, you can appreciate that this technology doesn't just replicate research. It transforms it into a competitive edge by significantly reducing development cycles and improving resource allocation.
Precisely. It's a win-win where technical excellence meets strategic business advantage, driving both innovation and profitability.
In my view, this approach is the future, a seamless integration of AI for generating reproducible, robust code directly from scientific literature, something that will redefine competitive standards in many sectors.
I couldn't agree more. As we continue to refine these processes, automation will help us focus on breakthroughs rather than bottlenecks, fostering a more dynamic and responsive innovation ecosystem.
That wraps up part 2 of our session. Thank you, everyone, for such an insightful and dynamic exploration into the technical and business facets of PaperCoder. Stay tuned for more discussions where we continue to unravel the cutting-edge intersections of AI and software engineering. As we wrap up today's deep dive, let's take a moment to summarize the end-to-end journey of PaperCoder and its groundbreaking impact on reproducible research.
To recapitulate, PaperCoder decomposes the research-to-code process into 3 structured phases: planning, analysis, and coding, mirroring agile development, and ensuring that every technical decision is traceable and well documented.
Right, and from a technical perspective, the key innovation is the multi-agent system that orchestrates each phase, enabling precise UML-based design, dependency-aware logic analysis, and nearly turnkey code generation with minimal manual intervention.
On the business side, what stands out is how this technology can drastically reduce R&D cycles, cutting down time and costs while increasing reproducibility. Imagine transforming a 2-month process into just a few days.
Absolutely. The integration of configuration-driven modularity means companies can seamlessly adjust hyperparameters and scale projects in real time, thereby supporting both compliance and rapid iteration in competitive markets.
And let's not forget the nuance of employing model-based and human evaluations. This dual approach ensures that the generated code isn't just theoretically sound, but also practically executable, evidenced by that impressive 0.48% average modification rate.
In essence, what we've seen today isn't just a technical marvel, but a comprehensive system design that bridges the gap between state-of-the-art research and real-world applications, enabling faster innovation without sacrificing rigor.
It's like having a well-oiled machine that takes scientific insights and directly transforms them into reliable, deployable code, empowering researchers and developers alike.
I'd also highlight the strategic perspective here. By automating these labor-intensive processes, organizations can reallocate valuable resources towards creative problem-solving and strategic initiatives, driving a competitive edge in today's fast-paced tech landscape.
And the potential applications span countless industries, from biotech and finance to manufacturing, where reproducibility and rapid prototyping are essential for staying ahead.
As we conclude, it's clear that PaperCoder symbolizes a significant evolution in how we approach scientific reproducibility, merging technical prowess with business agility in a way that truly redefines modern research practices.
In the end, the architecture and process we've discussed serve as a blueprint not just for code generation from research papers, but also for a future where AI-driven automation is the norm in innovation and development.
Thank you all for your insightful contributions. Today's conversation has provided an illuminating perspective on the intersections of automated coding, technical innovation, and strategic business transformation. Stay tuned for our next episode, where we continue to explore the cutting edge of AI applications in research and industry.